Hello everyone, my name is Avkash, and like me, if you have interest in reading research papers, digging through their implementation codes, and figuring out how things work, this video is going to be very interesting to you. Today, we are going to cover a very latest research from Google. It's LIMoE, or Learning Multiple Modalities from One Sparse Mixture-of-Experts Model. The promise behind LIMoE model is to process both text and images together using MOE layer, means a router, to tokenize the input and use a collection of multiple expert layers, each layer with a combination of experts to solve many problems. The biggest advantage of such architecture is to improve the model capacity in multi-fold while keeping the computational requirement to minimum as possible. We are going to look at LIMoE model architecture, its inner working, especially related with training, both text and image data processing through token and then router and then the MOE layer, and the performance evaluation with other competitive networks. So before I start this deep dive, I would suggest you to please review my previous video on MOE architecture, which is going to be very helpful to you because the core of LIMoE is the MOE. So knowing a lot more inner workings of MOE and its architecture is going to add a lot more benefit to you while you are going through with this LIMoE model. So let's get ourselves started. The LIMoE model is mainly the composition of MOE layer, or the mixtures of experts layer. Like any other sparse MOE models, it's a composition of two components. First one is the router and the second one is a collection of transformers. For a standard MOE, there will be multiple experts. In LIMoE, the single FFN is replaced by an expert layer, and that contains many parallel FFNs, and each of which is an expert, or we can call them individual experts. It means there are layers 1 to n and there are experts 1 to n. If the layer 1 is created, one or more FFN or the feed-forward networks are added. Similar to layer 1, the layer 2 is created, and slowly all the n layers are created. So the total number of active expert count is dependent on the total number of token counts. If the token count is smaller, then a few experts will be active, and they pretty much work like the standard transformer. Once tokens start coming at the router, the connectivity between the router and the experts layer level will be created, and the total number of experts layer will be depending on how many tokens are available at the routers, and the connectivity between the router and the feed-forward network will be managed through the backpropagation layer. And that connectivity will be keep growing depending on the total number of tokens are growing at the router and new export layers are being added. Finally, the results from these feed-forward network layers at every layer level, it means the output from multiple experts will be aggregated and sent to the dropout layer through the sigmoid function. And that completes the whole LIMoE layer inner workings depending on the total number of tokens arrived at the router and the total number of expert layers are needed to manage those tokens. Now let's see how the text and image data is processed inside the MOE layer during the training. And we are going to focus the training part depending on the results based on LIMoE architecture. So we already know that LIMoE models are designed for multimodality. It means both text and image data is processed together. The input data has to be tokenized first. So that is the tokenization layer. The data is tokenized at this point, and once the tokens are available, these tokens are fed to the MOE layer, where router is the first entry point to process these tokens. Depending on number of tokens available at the router, the number of expert layer or a collection of feed-forward networks will be active. And these tokens will be sent from router to individual expert layer, and the data will be combined. And as the training will grow more and more, the number of expert layers will be keep adding to meet the token requirements. And that is where the efficiency and the performance part comes. It means if the total number of tokens are small, not the full layers or the expert layers will be activated. Only those expert layers will be active which are needed to manage the incoming token requirements. And at this point, the tokens are being processed by these multiple parallel FFNs or the expert layers. While the training is going on, it is possible that all the tokens will be totally processed at FFN layer level, and the experts are becoming more and more expert in the individual part of incoming data. So the experts are performing the multimodal contrastive learning. So in the multimodal contrastive learning, the models are trained on paired image text data. It means the photo and its caption. So you have multiple images and their captions. They are being fed into at the start. And the image model is extracting the representation of images, and a different text model extracts the representation of the text. The contrastive learning objective encourages the image and text representation to be close for the same image text pair and the far away from the different pair. As the training progresses, these expert layer or the expert models with aligned representation, they can be adopted to new tasks without any extra training data, or we can call it zero shot. So when a new image will come and it will be classified as a particular object, in this sense we can take an example of a dog. So the new image came and it will be classified as a dog if its representation is closer to the representation of the word dog than the word cat. So the combination of both text and the images representations are used to classify the new incoming inference results. And slowly, the model or the learning or these experts can be extended or they scaled to thousands of classes or many thousands of classes, and that is what is directly equal to zero-shot image classification. Let's focus a little more about how we can learn LIMoE behavior or to understand the results from the LIMoE training. At the root of LIMoE was intuition. And the idea was that the sparse conditional computation is going to enable a generalist multimodal model. It means after the training, a generalist multimodal model will be generated to manage both text and the image together and to develop the specialization that is needed to excel at the understanding each modality, whether it's the text or its image. And the result does prove that intuition works with sparse conditional computations. While the deep learning researchers, they analyzed the LIMoE expert layers, they uncovered few really very interesting phenomena. And that's what you are seeing in the bottom of this image. After the deep learning researchers, they have added more and more text and image tokens that were being sent to these expert layers. All the experts, they started to process some of the text and the image tokens at the start. However, some of these experts, they were only focusing on image tokens or the text tokens. And that's what you could see, that some of them are just only experts in the hands. Some of them are experts in the patterns such as stripe texture or the solid textures. Some were focusing on individual items such as door handles or the plants or the exact words in given images, or being expert into the food and fruits, or the wider patterns such as ocean and sky, and many more. After the contrastive learning with LIMoE, looking at the model performance by comparing it with 4 different one-shot models, here both LIT and the basic models had the advantage of pre-training, while other clip, align and LIMoE, they were not used the pre-training. Both clip and align, they scaled the process to achieve about 76.2 and the 76.4 zero-shot classification accuracy on the popular ImageNet dataset. The other two, LIT and basic, they pushed the zero-shot accuracy for the dense two-tower models to 84.5 and the 85.6% respectively. Due to a specialized pre-training method with LIT and basic, they definitely had advantage over clip and align and achieved higher ImageNet accuracy. LIMoE H14 model has no benefit from any pre-training or the modality-specific components, but still it achieved 84.1% zero-shot accuracy training from scratch. One important thing to remember is that both LIT and basic, the parameter size was just almost double to LIMoH. Looking into the parameters per token, the LIMoH having just 675 million parameters per token makes it significantly more lightweight model. Finally, we can say that the multimodal models, which handles many tasks, is a promise development going forward, and there are two key ingredients for success. One is the scale, and the other one is the ability to process distinct tasks and modalities while taking advantage of synergies. And we can say the sparse conditional computation is an excellent way to doing it both. It enables performant and efficient generalist models that also have the capacity and flexibility for the specialization necessary to excel at individual tasks with less compute requirement. So that's all I had for you in this tutorial. I hope you have enjoyed the content in my video. If you have liked it, please do share it. Please subscribe my channel and also comment your feedback or any suggestions you have. I do appreciate your time and I'm looking forward to see you in my next video. Until then, please be good and do good. Thank you.